This is lesson 7.2, the triangle congruence theorems. So the big idea says the acronyms SAS, SSS, ASA, and AAS stand for combinations of measures of corresponding sides and angles in two triangles that are sufficient for the congruence of the triangles. So those big ideas are always wordy, coming from the textbook. But basically what we're going to be doing in this section is looking again at these are called congruence theorems. We're going to actually take it to that step and define the theorems. But these situations that we looked at in 7.1, where we have two triangles that have three matching sides, or a side and an included angle, meaning between it. In 7.1, we looked at maybe we're just given one triangle and could we create another one that was congruent. Now we're going to actually be looking at two triangles and stating whether they are congruent or not. And then we're actually going to spend a lot of time actually writing a proof and proving that two triangles are congruent to each other. And we have to use these theorems to do so. Okay, so just to quickly go over these, we already basically covered this in 7.1. The SSS congruence theorem, so now it's a theorem that we can use in a proof. If in two triangles, three sides of one are congruent to three sides of another, we know the triangles are congruent. We studied that in the first section. So now we can just say this one's congruent to this one because I have SSS. Okay, I know that these are the same size. That means all the corresponding parts are equal, all the angles are equal, all the sides are equal. Okay, SAS, same idea, but side angle side. Remember that angle, just like when we spell this out, the A is between the S's. That angle has to be between the sides. So I actually have these two sides that are equal to these two sides. And I can't just have an angle randomly out here somewhere to make this an SAS. It actually has to be between the two sides. So right where those two sides meet is also the angle that I know is congruent. So I can use that if that's what's given to me. We have angle side angle. Okay, so it's the side now is included between the angles. So it can't just be any two random angles. It's two angles and an included side. Sometimes that side is actually the same line segment. So we're going to start to look at triangles that either overlap or share a side, share an angle. Apologize for that. So looking at these triangles that either overlap or share a side, we know that side right there, like DE, is going to be the same for both triangles. So this triangle uses DE as one of its sides, and then this triangle, FED, also uses DE as one of its sides. So that can count. We're used to these ones that are completely separated. But if you notice in this picture, I know that this angle equals this one and this angle equals this one based on the markings. And even if this one wasn't marked, I can call this angle side angle matching. Both of these triangles would be congruent because they share that side. Therefore, that side is going to equal itself. If it's 5, then it's 5 in both of them. Okay, so we'll look a little more into that. We're going to see that again here. We also have the AAS congruence theorem, angle, angle, side. So as you work your way around the triangle, you have an angle, another angle, and a side that matches the other one. So C matches A. Both of these are 90 degrees, so they match each other. And then this, dropping down here, is part of ABD. It's also part of BDC. Now, if the measurement of that is 10 in one triangle, it's also 10 in the other triangle. So we don't need that measurement. So like here, they can either tell you the angles are equal or give you the actual amount, like 90 degrees. But here, they don't have to tell me that this is 10. They don't even have to mark it. If both of these triangles are using that segment as its side, I know that it's equal in both triangles. Okay, so we'll start using that a little bit more. All right, and the last theorem we're going to use here in our proofs is called your third angle theorem. It says if two triangles have two pairs of congruent angles, then their third pair of angles is congruent as well. For instance, over here, we already know that A equals C. We know that these two angles are equal to each other. So we automatically know that this one equals this one. Think about why that is. Let's just call this 60. Well, if that's 60, this is 60. The markings tell me they're equal. This is 90 and this is 90. Inside this triangle, take that away from 180. 90 minus 180 minus 90 minus 60. I know this is 30. Same thing over here. 180 minus 60 minus 90. This is 30. So I don't even have to go through the math and find out what that angle is. If I've got two angles of this triangle equal to two angles of this triangle, I automatically know the third angle is also equal. And I can use that in a proof by calling it the third angle theorem. All right, so let's jump into proofs. That's our main work here today. So we're actually going to have to start building these ourselves just for triangles, and they're really not that bad. So we basically have to just show these pieces equal to each other. Angles equal, sides equal, and now I can state that those two triangles are congruent. Okay, there's more than one way to do these, and so we're going to talk about that here. So we were kind of used to the given information being spelled out to us, and sometimes that will still be true, but we can take what's given in the picture and include that as our given as well. So here we go. First thing I'm going to do is just rattle off all the things I know that are congruent. So I know that this angle is equal to this one, or congruent, because they're both labeled 47. So what I'm going to do is I'm going to say angle A is congruent to angle T. Now, I'm going to list more than just that because I have more given information, but everything that's in this list separated with commas is part of the given. It's in the picture, so it was just given to us. We didn't have to figure it out. Okay, B is going to equal, angle B is going to be congruent to angle U because it was given to us in the picture, 103 and 103. And then also, I know this side equals this side. Those are segments. BC is congruent to. And when you're naming a segment by itself, it's not as important to get everything matching. But if you notice, if I'm calling this BC, I was going from the 103 away from it. So really, I should match this one up the same, the corresponding pieces. So I'm going to name this one, instead of VU, I'm just going to go the other direction, UV, so that for BC, I went from the 103 away from it, and then from UV, I went from the 103 away from it. Now, specific to just the side lengths, it's not super important, if I'm being honest. But when we name the triangles, it is important to match up the corresponding angles as we go around, and we'll talk about that here. Now, let's look at what we've got right here. We've got an angle. I'm going to label it angle. I've got angles, and I've got sides that are equal. And if I look in the picture, as I read my way around, it's angle, angle, and then side. Angle, angle, and then side. So I already have enough information to use this theorem to prove that these are congruent. So this can be a very short proof. So now I'm just going to state this triangle is congruent to this one. So triangle, you actually put the symbol. ABC is congruent to triangle. And now here is where you have to match this up. Because remember these congruent statements, you actually have to have the corresponding angles in the corresponding spots. So angle A matches angle T. So I have to put T in the first position because A was in the first position. B matches U. Okay, so U has to go here. So the middle letter is the 103 in both of them. And then that leaves me with V. So triangle ABC is congruent to triangle TUV. And your justification is just that theorem, angle, angle, side. And technically you would put theorem, but we're just going to put that. That's fine. Now, there's more than one way to do these. You only need to show one if this is a problem that you have to solve. But let's talk about how we could do this differently. And we wouldn't necessarily. This would be the shortest way to do it. Everything was already given to you. But I could solve this by something other than angle, angle, side. So let me show you what that would look like. So this first part, you would actually have all of that there. I'm not going to rewrite it for the sake of time here in the notes. But that's all given. And of course, if that's all given, then I could just say that these are congruent by this. But just to do it a different way, if I have two angles, two sets of angles that are congruent to each other, I automatically know the third one is also equal. That's my third angle theorem. Right, I could go through the math and do 180 minus these two, get this angle, and it would be the same in both. So clearly C is going to match V. So I can write that here. Angle C is congruent to angle V. And the reason is the third angle theorem. So that, I just wanted to show you how we're going to use that theorem. You've got two matching angles. The third one's automatically matching by the third angle theorem. All right, and now that I know that, if you take a look at the picture, I've got the 103s matching, I've got these matching, and I've got the side that's in between those matching. So I don't need to use the 47 here. I've got angle, side, angle. So now I can state, again, this would have to match up. So ABC is congruent to, I haven't changed anything, so it would still be TUV. But the way I've proven it now is by SAS. I'm sorry, I just read that backwards. Angle, side, angle. ASA. And what you heard me just say out loud, that's really easy to do, is just write down the wrong combination here. So just always be careful, double check yourself. It's really easy to just write down AAS when you meant ASA or something like that. So just be careful. And you need to make sure that it's actually one of these. Okay, if you notice, ASS, which I'm sure people have already thought of, is not one of these. And the reason isn't because it spells out what we would consider to be a cuss word, ASS. It actually doesn't work. If you have two sides and then an angle that's not included on it, it doesn't prove that those triangles are congruent. Okay, you could come up with different triangles that have two matching sides in a matching angle that's not included, and show that they're not congruent to each other. So ASS is not a congruence theorem. And again, it's not because it doesn't spell out a cuss word. It's because it doesn't actually work mathematically. So make sure that you're actually using one of these congruence theorems that is given to us here. Okay, to the back. So for these, you're going to see this style in your homework tonight as well. We don't have to write a whole proof. Okay, we're going to use the diagram to tell which triangles are congruent. So on number 4, that's obvious, these two triangles. But then as we start showing these more complicated pictures, we need to actually clearly state which are the triangles that are congruent to each other. We're going to write a congruence statement that indicates the corresponding vertices, just meaning when I write, for instance, BCA is congruent to this one, I need to make sure that I put these in the right order so that corresponding parts match up, just like we did in the proof on the last page. And then I'm also going to state the theorem that justifies it. That's your SSS, SAS, all that stuff. Okay, so clearly these two equal each other. I have angle matching angle, angle matching angle, side, angle, side is a good one. So that's part 2 over here. This is angle, angle, side. Triangle, I'm just going to go around. You can put this in alphabet. You could call this ABC if you want. I guess let's just do that for the sake of it. Triangle ABC is congruent to, and now you can't grab random letters. You have to put the matching corresponding parts in the same position. So A matches N, so I have to put N first. B matches Q, and then C matches F. So the order does matter. Okay, number 5. I've got a side matching a side matching a side, and then they share the third side. So clearly that is going to be equal if you wanted to mark it. You couldn't use the 1 or the 2 because then you'd be saying that that side matches these as well. So I use 3 to show that this matches itself. So this is SSS. Let's go ahead and name this. I'm going to go, again, it doesn't matter how you start the first one as long as the second one matches. So I'm going to start at X, go to Z, and then to W to name this one up here. So XZW is congruent to, X is going to match Y. And notice I went across. You can use the markings to help you as you name this. I went across the side with one marking. So if I'm starting at Y, I'm going across that one to Z and then to W. Okay, and then in number 6, I've got 3 different triangles here. The 2 that are going to match is this one and this one. I've got enough information because I have these sides are all equal to each other. These are isosceles triangles, okay, and they're going to match. Since they all have one slash, I know that not only does this match this, but it also matches this and this. All 4 of these would be the same. So like if this was 10, they'd all be 10 because they have the same marking, whereas sometimes there's 2. So yeah, that matches this and this matches this, but here they all match because there's just one marking. So be careful with that. This angle matches this angle. It's between. This is an SAS matching an SAS. Okay, so now let's name those. So I'm going to go E, N, P, and I'm talking about a triangle. I need the triangle symbol. Matching E is A. And now you actually have options on this one if you want to get into the weeds on it, because so I went from E to N. You really don't know which way this goes because this is an isosceles triangle. I'm going across the 10. So if I go from the A going across the 10 in either direction, these angles are all going to be equal to each other because I've already proven that these triangles are congruent. And in an isosceles triangle, we know that these interior angles, base angles, are equal to each other. So because of that, I know all 4 of these angles are also equal. And so as I name this, the A does go with E for sure. That's the vertex angle. But since the base angles are the same, we don't actually know which way this goes. So the order is not going to matter. Whether you say APT or ATP, it doesn't matter. All right, another proof here. This one's going to be similar to the one we did on the front. So as we jump in, first thing we want to do is put everything that's given. So I know angle N is congruent to angle Q. I need the angle symbol there. I also know that angle M, is congruent to angle P. And I also know these sides are equal to each other. So NO is congruent to QR. All right, so I already have enough information to prove. I've got an angle, and a side, and I need to make sure they're in the right order. Angle, angle, side, they are. Okay, so I could jump straight to my conclusion. I'm going to go around, so from the 55 to the 40 to the other one that I don't have. So N, M, O, match it up on the other side, 55 to 40 to the missing one. So Q, P, R, and again, that's triangle QPR. All right, and that was by angle, angle, side. And I'm not going to go through the whole exercise again, but it would be very similar to this one. We could use our third angle theorem and then ASA here. We could say, well, I know these 2 angles are equal and these to these 2, so clearly R equals O, and then that creates an angle side angle. So we could show the proof that way as well. For the sake of time, though, I'm not going to do it both ways. Just know that you could. All right, and then to the last one. This one's a little different now. All that we're given here is that this is a parallelogram, and the line from P to R is a diagonal, meaning it hits P and it hits R. So our first line that's given to us is just the fact that this is a parallelogram. Now think about, how do we use parallel lines? We're always talking about corresponding angles, alternate interior angles, same side interior, that kind of stuff. That's what's going to help us here. So if this just looks like a parallelogram, I can't start saying, oh, these angles are equal because they're alternate interior. I have to know for sure it's a parallelogram, either through markings in the picture or it was given to us. So, and I can't start saying that alternate interior angles are equal until I state that this is a parallelogram and that I state that these sides are equal. And this is where proofs can get a little nitty gritty, because you're already kind of jumping to those conclusions in your head. But in a proof, a formal proof, you have to state all of that. It's kind of like you're a lawyer and you have to state everything, even though it seems obvious, it still has to be put down on paper. So I know that PARL, the shape PARL, is a parallelogram because it was given to me. It's right here. Okay, that's the only reason I know that. The picture does not tell me, but it was given to me here. Because I know it's a parallelogram, I know that this side is parallel to this side, and I know this side's parallel to this side. Now, where that's going to help me is I'm going to be able to use these alternate interior angles and say that this angle equals this one. But I can't say that until I've actually shown that these are parallel. So this is a parallelogram. So because of that, I know that AR parallel is this symbol. AR is parallel to PL. And I can shove this all in one line here. These are parallel as well in a parallelogram. So AP is parallel to RL. Notice I'm not too worried about the order there. I'm just stating the segments. So no matter which way I read it, it's still the same segment. They're still parallel to each other. So I didn't get all worked up about which letter goes where. So AP is parallel to RL. The reason I know that, how do you know that? It's because they told me this is a parallelogram. So the definition of a parallelogram says that opposite sides are parallel. So that's how I'm able to say these are parallel, because that's the definition of a parallelogram. So first, I needed to be told it's a parallelogram. From that information, I can say the sides themselves are parallel. Now I can start saying that these angles are equal. So if I've got parallel sides here and it's being cut by this line, these are alternate interiors, so they are equal. So angle ARP, that's this one, follow it around, ARP is congruent to RPL. And if you named these backwards, it's fine. Angle RPL. Remember that the vertex is the important part. So if you switch the R and the L, no big deal. That's where the angle is. Got to be the vertex. Now, this is alternate interior angles. And if you wanted to then go and do number 4 and do your other angles that are going to be equal, this one is going to be equal to this one because of this parallel side, right, being cut. Those are also alternate interior. Since you're using the same justification, just like I put two things here, they were both justified by the definition of a parallelogram. I can put this all on line 3. If you wrote another line 4 and you said this one equals this one because, again, alternate interior, that's not wrong. But you can put it all into one line and use one justification for both. So now I'm going to say that this angle here, APR, is congruent to this angle right here, angle PRL. And again, since it's on the same line, it's also alternate interior angles. Now look at what I've got. I've said that I've got a set of equal angles. I've got another set of equal angles. Right now, that's it. I can't prove that these triangles are congruent to each other with just two sets of angles. We talked about that in 7.1. Just having two matching angles doesn't mean they are the same triangle. I haven't been given any other information in terms of side lengths. Now, you could use the fact that we know certain things in parallelograms are going to be equal to each other. So we could use the definition of a parallelogram to state that these other sides are equal to each other. But the one that I want to focus on in this, and that wouldn't be wrong, you could do it that way. But the one I want to focus on is this shared side, because I think that's the one that's actually easiest to use. So this triangle APR and this triangle LRP, they both have this side between R and P. And so that side obviously matches itself. You could redraw these separately. So here's R, L, P, this triangle right here. And then you could separate this one, A, R, P. And notice RP has to match RP. So if you separate it, you can see it's the same line. So they're sharing it. So we're allowed to use that in our proof. So I'm just going to state that RP is congruent to RP, once from this triangle, once from this triangle. And that's when you're going to want to get used to. That's your reflexive property. Anything is equal to itself. But if I'm going to get to the end of a proof and I'm actually going to say this triangle equals this one by angle, side, angle, or whatever it is, those have to be in my proof. Okay, I can't just do these angles and then jump to my conclusion and say angle, side, angle, just because I'm assuming that or whatever. It has to be stated. That's what I'm trying to get at. So here's a set of equal angles. Here's a set of equal angles. I can't actually say these are congruent until I state that I've also got a matching set of sides or whatever it is. Okay, so they all have to be spelled out, which is the annoying part of a proof. I get it. Okay, but it has to be spelled out. So now we can say that this triangle, let's go ARP, is congruent to, A is going to match L, so triangle L. And since I marked these angles, this is easy. So I went to this one, which matches this one. So L, P, R. Notice this R right here in this triangle, the blue right here, matches the P in the other triangle, the blue. This third one in this first triangle is marked with the two red ones. That P matches angle R, these two red ones here. So I've got this in the right order. And if I just work now, you go back to one of these triangles, I've got my angle, and I've got my side in between them. So this is A, S, A. Okay, so that's the basic process for building one of these triangle proofs. We will get lots of practice on these, and they will become second nature.